The next model that I want to look at is an electronics enclosure. And the challenge for the electronics enclosure is to determine the best cooling fan location. So if we look at the model itself, we have two inlet vents on the one side. We have an outlet through the fan, so the fan's actually sucking the air across the components. It does have integrated circuit temperature. We want to look at flow across the enclosure. Heat transfer characteristics, so how does heat build up and transfer through the components, not only conduction but also convection? How is that fan taken care of in removing the heat? And the goal itself is that the internal circuits, or the circuits that are underneath these two coolers or heat exchangers, stay below 100 degrees Celsius. So again, in order to do that, we're going to look at four different options: a left, middle, and right fan location, as well as a dual fan location. And after looking at these, what we're going to see is chip 1 and chip 2 are really what we're trying to obtain, and both of them have to stay below 100 degrees C. So with the fan in the right location, chip 1 stays there, chip 2 does not. With the fan in the left, we have 92 and 95. In the middle, 91 and 98. And of course, with two fans is the best option, which is 80 and 86, but that may not be cost conducive. We have to cut a whole new set of holes, or laser cut a new set of holes in that end for a second fan, the cost of the second fan. So really the left and the middle options are our two viable locations. So let's switch back to SolidWorks and change to that model. Now the setup of this is very similar to the ball valve setup. I went through the wizard to start with. The boundary conditions, though, have changed just a little bit. And those changes are really evident here. And if we look at our configuration, we're going to start off with the left position first. And if we look at our flow tree, the difference here is I turned on conduction and solid, so I had to specify materials. Some of these did carry over from SolidWorks, other ones I did have to specify. But these materials then carry with them the conduction or thermal conductivity components or parameters to describe how is that conduction taking place. Environmental pressure at the inlets. The other option here is a fan curve that was added. So if I look at my fan curves, one of the nice things is we gain a wide variety of different fans and curves that we can add. So axial fans, specific fans curves for AC and DC components, different series. So radial fans as well. So we have a very large list of fans that we can actually go through here and choose from. So we found the specific manufacturer of this fan in that list and applied that fan curve. The only other difference between this and the ball valve is that we have a heat source. So each one of these chips that are underneath the heat exchangers, or the cooling fins, is generating 10 watts of heat, as well as this capacitor. Our transformers are generating 4 watts, and our other capacitors are generating 5 watts. And just to make note here, I did simplify the model so you do not see all the routing lines or the wires. Some of these smaller capacitors and resistors are indeed suppressed. This is for a first pass. I will show you the model with the full run. From here, my goals are just that my temperature in the solid across both of these heat fins, or these cooling fins. So let me reload the results of this one, and we can take a look at what we received here. So I can show a velocity plot or cut through. So this is showing us how is the part reacting, or how is the fluid flow going through or into these vents, around the components, through the cooling fins, and then down and out through the fan. So we get a good understanding of how is this flow actually moving around these components. I can change this actually to fluid temperature so we can see the temperature of air moving through this, so we can see that the temperature on these cooling fins, or of the air around the cooling fins, is actually rather hot on the back end of this capacitor and kind of on the front end of these capacitors as well. I can probe this as well. If I turn on my probe tool, I can actually get a live preview as I move through here of what are those temperatures. So I can see 90.86, 90.82 in the area in between these fins. I can also look at a surface plot here. So if I show a surface plot, this is the heat transfer coefficient. So if you do not know what your heat transfer coefficient is, and it always varies per geometry. So this would indeed be a forced convection type problem, but is it 10? Is it 20? Is it 30? We don't know. And actually what we see from flow is that the heat transfer coefficient can actually vary per geometry across different boundaries on the geometry itself. So we actually have, if I probe this, a higher heat transfer coefficient, 37.09 watts per meter squared degree Kelvin, at the top of this capacitor, but at the bottom we're at 14. So this actually gives a very good understanding and relates back to the flow of how is the heat being transferred off of this, instead of just picking the entire body and saying, you know what, is forced convection, we're going to specify 14 or 20. It's not as accurate as actually having it calculated by flow. So I can hide this. Let's look at the solid temperature, so the actual temperature gradient across these solid components. So we're working here, and we'll see this plot come up here in a second. But the solid temperature, again, is a surface plot, and it's going to cover or show us a surface map of the temperature on these components. So it's generating the plot, and what we can see here is these capacitors have a different temperature gradient. Our transformers are right about 66. This larger capacitor is at 102, and we can see the difference between the two chips, so 91 and 94. Last thing that I want to show you here is indeed the flow trees through this enclosure. And we can actually animate these. Now this is colored by temperature. Let me change this to velocity, and we can play this as well. So you can see as it goes in how these are actually wrapping around and manipulating. Let me actually stop this and change this here back to pipes, because that seemed to display a little bit easier across the webinar. And let me animate this guy now. So you can see the flow coming in the vents and kind of recirculating around. It's a little choppy on the webinar. I apologize about that. So that's in the left position. Let's switch to the middle position. That was the other position that looked viable for us. So all I have to do is change my configuration. It does take a couple minutes here, but you can see that the fan did move to the middle. I can switch into flow, load my results for this, and what I want to look at is the solid temperature of these guys. So let's go ahead and show this plot here. This may take another minute just to generate the plot. But what we'll see is the temperature across both of these should relate or come back to being the same as what we see on our spreadsheet here. So 91 and 98 accordingly. So the left and the middle conditions are what we want to look at. Again, this was first pass, so what we're going to do after this is look at the model with everything or all of the components across it, and then view the temperature curve or the velocity cut plot to see what we gained from that. See if it did essentially affect the two. But if we probe this, we're at 98 and 91 on these components. So we're looking pretty good for middle and left. So at this point, the next step is actually to run this with with everything in the cabinet. So I'm going to look at the left. This will actually have all the smaller capacitors. It'll have all the route lines with the wires. So we want to see, all of those components do affect the flow, how the flow transfers through. So we want to make sure, just as a final pass, that with everything in the enclosure, that we're not getting different results than what we saw in the simplified model. Okay, looks like it loaded here, and again, I apologize about that that delay. But let's go ahead and look at the results here on the full model. Now what you're going to see, the middle is actually the best run, but what I want to show you here is if we show this with the full model, just wanted to show you the difference in velocity that you can see. And what we're gaining from this essentially is, with these extra components, we're seeing a vast difference in that velocity. Before, it was a really nice straight curve coming down in. We're seeing that these smaller resistors or capacitors are actually blocking that flow from reaching this larger capacitor. So, at this point, it's always best if you run it with the full assembly at the very last or at the very end. Let me hide velocity here, and let me show the solid temperature. And what you're going to see with this is, with the full model regarding the solid temperature, the middle fan looked, the left fan looked very good from our initial results. But what we're going to see here is actually that we go above the 100 degrees C because of the additional components that are kind of blocking the flow from those heat exchanger fins. So at the end of the day, you always run the full model just to verify the results, and what we saw from this one was the middle is actually the best one to run. So once the solid temperature comes up, we'll do a probe on that and take a look. Again, I did have goal plots here, so I could export my goal out to Excel as well to see what is the temperature on that component. So we have that ability. So, and again, I apologize. It's hitting my CPU pretty hard here. But any questions up to this point? Okay, actually one of the questions is, can you enter your own fan curve into the fan module? That's actually a very good question. Yes, it's fully customizable. So if you have that empirical data from the fan, either from the fan manufacturer and it's not one that's in the list, or you did that testing yourself, let's say you set up pitot tubes and pressure sensors and everything else to get that kind of data, yes, you can enter that in, and I'll actually show you that here in a minute where you can do that. But this is the full model. If we look at a probe now, what we're going to see is we're above the 100 degrees on one of these chips, on the right-hand chip. And that's again because we've got blockage of that flow here. So the middle option is actually the best one as opposed to the left option. So even though they both looked good from the initial standpoint without everything, from this point, it's better off to go with the middle one. Let's address the fan curve here. If we go into and edit the definition of this, we can do create and edit. And what this brings up is our engineering database. And in here we have an area where we can make a user-defined fan curve. So in general, we usually copy one of the existing, place it in the user-defined fan curves here. And so I have one actually that was generated here, so original flow. So this is one that wasn't available, so I added this. We look at the item properties, what is the reference density, volume flow rate, the value. Here's my table. So this is my volume flow rate per pressure difference, and I added this in. This actually came from Excel, and I pasted it into here. So yeah, most definitely you can add any fan curve that you want. Same thing for any of the material properties as well.